A Magnetar flare is a single cosmic flash that can outshine our entire galaxy. It's a magnetic explosion of almost impossible power. A dead star the size of a city can, in a millisecond, unleash more energy than our sun produces in 100,000 years. We're going to go inside these stellar corpses to see what twists their magnetic fields into knots of pure cosmic violence. How matter can even exist under such extreme conditions. And what would happen if one of these eruptions happened closer to home? That supernova flash, that final burst of light. It's not the end, it's a change. A violent one, a star much bigger than our sun, reaches its end, and it doesn't fade away. Its core runs out of fuel, the fusion stops, and without that outward pressure, the core just collapses. In less than a second, the outer layers explode outwards. You can see that across galaxies, but what's left behind is something else. The core gets crushed down. Maybe to a sphere just 12 miles wide. That's a neutron star. The material is so dense, a teaspoon of it would weigh billions of tons. This is matter pushed to an extreme. Atoms are gone, protons and electrons are forced together. Just a sea of neutrons, but among these stellar remnants, there's one that's even more volatile. The Magnetar, it has that same impossible density, but it has something else, a secret ingredient. It becomes the most magnetic object we know of. It happens during the collapse. The core spins up hundreds of times per second, and the star's internal magnetic field gets wound up, amplified, concentrated. The result is a magnetic force. A quadrillion times stronger than Earth's field. Saying it's strong is an understatement. From 100,000 miles away, that field could erase every credit card on Earth. This isn't a quiet rock in space. It's a titanic spring, wound up with pure magnetic energy. The whole star is under strain, unimaginable strain. Its crust is solid. A lattice of iron nuclei, 100 trillion times denser than steel, and that crust is constantly stressed, fractured by the forces inside. It's like a cosmic pressure cooker. The lid is rattling, held down only by gravity. All that twisted magnetic energy is pent up. It's searching for a way out, and when it finally escapes, the universe feels it. That solid crust finally gives way. It's a starquake. The ground is a lattice of iron, 100 trillion times denser than steel. Like tectonic plates, but these plates are the entire surface of a dead star under this unimaginable magnetic pressure. And when they shift, they don't just rumble, they crack open the star's magnetic prison. That's the trigger, the moment everything's been waiting for. Inside that crack, the magnetic field lines they'd been twisted into impossibly tight knots, they suddenly snap. They break and reconnect. A new, simpler configuration. That process is magnetic reconnection. It's like the ultimate cosmic short circuit. All that pent-up magnetic energy, stored for decades or centuries, it has to go somewhere. Instantly, it can't be contained, so the energy converts. It doesn't burn, it transforms directly. Magnetic force becomes raw particle acceleration, intense radiation. The violence of the reconnection, it rips electrons from the star's surface, flings them out at nearly light speed, and these electrons smash into the twisted magnetic field. That collision creates a secondary burst, produces pairs, particles and antiparticles, electrons and their antimatter twins, positrons. In a millisecond, the fracture zone becomes a fireball. Pure creation and destruction, a temporary hell of gamma rays and X-rays. This isn't an eruption, it's a rupture, a single, blinding flash. Energy so concentrated it makes a supernova look slow. Deliberate, the entire cataclysm from the starquake to the peak of the flash can be over in less time than a single heartbeat. But in that instant, the Magnetar unleashes a fury. It dwarfs the steady output of our sun for millennia, so the question is how much energy. The numbers defy any earthly comparison. The sun is a steady furnace. It puts out 3.8 times 10 to the 26th watts of power every second. That flow has been constant for billions of years. Now take all that energy. Every bit of sunlight that's ever hit the Earth, collect it not for a year, not for 1,000 years, for 100,000 years, bundle that entire epoch of solar output into one point, and release it all at once, in less than a millisecond. That's the lower end of a Magnetar flare. The numbers are too vast, 10 to the 39 ergs. 10 to the 45. An erg is a tiny unit, but the exponents are meaningless. A better analogy is violence. Imagine the surface of that city-sized star. Cover every square inch of it with 1 billion of the most powerful thermonuclear bombs ever built. Then detonate them all at the exact same moment. That cataclysm isn't fire and sound. It's a silent scream of pure radiation. Hard X-rays and gamma rays erupt from the fracture. This isn't light you can see. It's light that can pass through feet of lead. Light with enough punch to strip molecules apart, to rewrite the very code of life. It's the universe's ultimate blowtorch. For our minds, built to understand the world around us, these scales are a form of madness. They push past comprehension. So how do we know such things are real? How did we move from theory to recorded fact? The answer isn't in our eyes, it's in our instruments. Silent sentinels orbiting Earth that were suddenly blinded by a light from the depths of time. On August 27, 1998, the universe sent a message. It wasn't a whisper, it was a roar coming from 20,000 light-years away. Observatories were out there, the Rossi X-ray Timing Explorer, Beppo SAX, just doing their work. And then their sensors screamed. A wave of radiation hit them, so intense it flooded the detectors. It forced a shutdown, a protective one. The source was a point of light, something already catalogued. SGR 1900 plus 14. But in that moment it became something else. It was the first giant flare from a Magnetar, the first one we ever recorded, and it was undeniable. The signal had a signature, an initial spike of power over in a fraction of a second, and then something strange followed it, a pulsating tail of energy that faded over minutes. That tail was the key. It was the dead star itself ringing like a bell. A catastrophic quake had happened, and its intense magnetic field was modulating that fading glow. Theory met reality. The data was right there. In that single flash, this object outshone every other star in the Milky Way for a brief moment. Its luminosity was calculated. It was 100 times greater than the total light output of our entire galaxy. The scale of that, a single city-sized ember from a stellar funeral long ago, became the brightest thing in a galaxy. A galaxy of hundreds of billions of stars. Textbooks had to be rewritten. Skeptics were silenced. This wasn't an anomalous blip, it was a declaration. It proved Magnetars were real. They were active and terrifyingly powerful, and they were inhabitants of our galaxy. The 1998 event was a turning point. It forced us to look at the sky with new eyes. The cosmos isn't a quiet, serene place. It's punctuated by these eruptions, sudden, catastrophic ones. And so the task shifted. It shifted from wondering if they existed to hunting for them, to cataloging these sleeping giants, to listening for the next Starquake. The one that would tear the silence of space apart. 6 years later, we got another reminder. On December 27, 2004, a Magnetar called SGR 180620 erupted. It was 50,000 light-years away on the far side of the galaxy, but for 0.2 of a second, it was the brightest thing ever seen outside our solar system. It released more energy than our sun will put out in the next 150,000 years. The flash was so intense, it outshone the full moon for an instant. So bright, astronomers saw its light reflecting off the surface of our own moon, a ghostly echo from across the cosmos. Spacecraft that watch for nuclear explosions on Earth were triggered. Their sensors were overwhelmed by a source not from our world, but from the galactic core. The radiation was so powerful it punched through the void and struck our planet's upper atmosphere. It ionized the air above us, causing a sudden, measurable disturbance in the ionosphere. A star that died millennia ago, on the other side of the Milky Way, reached out and physically touched our sky. It showed these eruptions aren't just brilliant lights in a telescope, they're events of interstellar consequence. If this had happened closer, within 10 light years maybe, the effects would have been catastrophic. The ozone layer could have been stripped away, exposing life to a lethal bath of ultraviolet radiation. The Christmas star of 2004, that's what they called it. It was a wake-up call. It changed Magnetars from fascinating oddities into a genuine point of concern. It forced a new line of questioning. How often do these sleeping giants awaken? And what are the odds one exists close enough to be a threat? That event in 2004, it forced a new vigilance. We had to find them before they flashed. We had to map these sleeping giants in our galactic neighborhood. It's a cosmic census, but not with visible light. It's done with X-ray eyes, gamma-ray eyes, because these dead stars, they're often invisible, cold and dark to optical telescopes. But they give themselves away. They have this persistent high-energy glow, a simmering X-ray aura. It's powered by the slow decay of those monstrous magnetic fields. So satellites like NASA, a swift observatory like New Star, they scan the skies. They listen for that specific whisper. They're hunting for two signatures. The first is that steady, hot glow. The second is the occasional, softer sputter. The small bursts, the flares, that's a crust under stress. Those are the soft gamma repeaters. The SGR, that's where the class gets its name. Through this painstaking work, we've built a catalog. Right now, we know of about 24 confirmed Magnetars in the Milky Way. And a handful of suspects. It seems like a small number until you consider the math. Each one we see is active. It's in that brief, volatile phase of its life. That phase might last 10,000 years, but the galaxy is over 13 billion years old. So for every active Magnetar we spot, there must be thousands. Even millions that have gone silent. Their magnetic fields have finally decayed. They leave behind a dormant neutron star. They're the ghosts of stellar cataclysms past. Drifting unseen through the spiral arms, confirming a candidate that takes detective work. Astronomers clock their slow spin. They measure the gradual lengthening of their pulse. That's magnetic braking, sapping their rotation. They analyze the light itself. They search for a telltale dip, a cyclotron line. It's a direct fingerprint. An electron spiraling in a magnetic field so strong it leaves a mark on the radiation spectrum. Each new identification is a triumph. It adds a data point. It helps us understand how often massive stars die in this particular twisted way. It helps model their life cycle, from supernova to hypermagnetic youth to quiet old age. This census isn't just academic, it's a risk assessment. By estimating how many of these objects exist and where they might be, we can start to calculate the probability, however remote, of one awakening too close to home. And that thought, it turns our gaze back from the galactic map, back to our own pale blue dot, to a very practical question. And an unsettling one. The Christmas star event showed these flares aren't just lights in the sky, they're physical forces that can travel through space. Which makes you ask a question: could a Magnetar flare ever actually threaten life on Earth? The answer has two parts. One is physics, the other is distance. For a true global catastrophe, the conditions are very specific. The Magnetar would have to be extremely close, maybe within 10 light years, and it would have to fire a giant flare right at our solar system. In that case, the first wave of X-rays and gamma rays wouldn't be what kills us. Our atmosphere would take that hit, but in taking it, the atmosphere would change. That high-energy radiation would tear apart nitrogen and oxygen. It would start a chain of chemical reactions. The end result would be the loss of a huge part of our ozone layer. That shield, which blocks the sun's harmful ultraviolet rays, would be broken. Then the surface would be flooded with lethal UVB radiation for months. Maybe years. The effect on the biosphere would be catastrophic. It could cause a mass extinction. It could reshape life on the planet. This isn't fiction. It's a physical possibility, but then there's the context, and the context changes everything. The closest known Magnetar isn't 10 light-years away. It's thousands of light-years away. Given what we know now, the odds of that perfect nearby disaster are almost zero. Across human history, it's not a real risk. The universe is enormous. These objects are powerful, but they're rare, they're scattered. The more realistic danger isn't to our bodies, it's to our technology. A strong, aimed flare from a Magnetar a few hundred or thousand light-years out wouldn't hurt us physically, but it would send an electromagnetic pulse through the solar system. That pulse could create powerful currents in our upper atmosphere, in the circuits of our satellites. It could fry sensitive electronics. We could have a global satellite blackout. Instantly, GPS would go down, communications could fail, power grids might surge. It would be a massive shock to our civilization, a reminder of our fragility. Not as living things, but as a technological society. That's why astronomers watch these objects, not from panic, for preparedness, studying their cycles, mapping their locations. It's like cosmic weather forecasting. It lets us see the balance we're in. We live on a small, life-filled rock, in a galaxy that's still being shaped by these violent outbursts. They're part of the galaxy's life cycle. They might even influence star formation somewhere else. Our being here is a kind of luck, and it comes with a responsibility to understand the forces that surround this quiet corner of space. There's a deep irony in that kind of power. The same flash that could wipe a planet clean from light years away, it's also an engine of creation. That duality is built into the universe. Chaos and order aren't opposites, they're partners, and a Magnetar flare is one of their most dramatic collaborations. Take a giant molecular cloud, a stellar nursery light years across. It's cold, dark, quiet. The gas is so diffuse, gravity alone has trouble pulling it together to make new stars. It needs a push, a shock wave. For a long time, we thought supernova were the main architects. Their blast waves would plow into these clouds, compress pockets of gas until they collapse. But a Magnetar flare, it's different. It's a more focused jab. More violent, the eruption doesn't just send out light, it propels a storm, high-energy particles, radiation, moving at nearly light speed. This jet, if it hits a nebula at the right angle, it acts like a cosmic hammer. It slams into the cloud. The impact creates a shock front of incredible pressure, rippling through the gas, and in that compressed region, gravity suddenly finds its advantage. The dense knot begins to contract, to heat up. A protostar is born, so a single cataclysm of death can midwife the birth of countless new suns, far across the galaxy. But the creation goes deeper than that. It goes into the elements themselves, all the gold in jewelry, the platinum in a catalytic converter, uranium in power plants. These heavy elements, they weren't forged in the steady heart of a star. They were born in moments of unbelievable violence. One leading theory points to neutron star mergers. But Magnetar flares might also play a role. The environment during a flare is a neutron-rich maelstrom. As the star's crust shatters and the magnetic field reconnects, it creates a torrent of free neutrons. In a process called rapid neutron capture, atomic nuclei get bombarded. They gobble up neutrons faster than they can decay. That builds atoms up the periodic table, step by frantic step, all the way to the heaviest elements. The flare, in its furious passage, could be seeding space with these new atoms. Later, they get swept up into new clouds, incorporated into new planets. Maybe even into the chemistry of new life. So this stellar corpse, this avatar of pure destructive force, it becomes a cosmic crucible. It takes the simple ashes of a dead star and transmutes them into building blocks of futures we can barely imagine. It's both an end and a beginning, a reminder that in the grand narrative of the galaxy, destruction is rarely an absolute. It's usually a transformation, a scattering of seeds. To really understand how matter behaves in a laboratory that extreme, you have to go to a place where the normal rules of physics aren't just bent. They're rewritten. To understand a magnetar, you have to go inside, and inside, reality stops working. The magnetic field there, it's not just strong, it warps the quantum vacuum, the empty space between particles. That's called vacuum birefringence. Normally, light vibrates in all directions, but under that magnetic grip, the vacuum acts like a crystal. It polarizes light. So the void isn't empty anymore, it has a structure. Pure force gives it shape, and that force reshapes matter. An atom is usually like a tiny solar system. A nucleus, electrons in fuzzy orbits. Here, the magnetic field is so intense it overpowers the electric forces. It stretches the electron cloud into a long, thin cylinder. Chemical bonds, the handshake between atoms, they become meaningless. They can't exist. The architecture of material reality just comes apart. Then you go through the crust. The surface is a solid lattice, but not of atoms. It's a grid of atomic nuclei, mostly iron, in a dense sea of electrons. It's 100 trillion times denser than steel. But under the strain of the magnetic field, it's brittle, like a mountain range made of diamond, constantly cracking under its own weight. Those fractures are the starquakes. They trigger the flares, go deeper. Below the crust, the pressure is so great atomic nuclei dissolve. You enter a superfluid sea of neutrons, a quantum liquid with zero viscosity. It flows without any friction. In that sea, even stranger phases might exist. Protons could form superconducting currents. At the very core, the neutrons themselves might break down into a soup of quarks and gluons, a state of matter not seen since the first microseconds after the Big Bang. This whole interior is a colossal engine. The slow decay of the magnetic field heats it. The differential rotation between the superfluid interior and the solid crust stresses it. It's a perpetual motion machine of pent-up energy, all inside a sphere no wider than a city. It's the ultimate physics laboratory. Conditions so extreme they test the laws of nature. They probe the edges of our standard model. We can't recreate this on Earth. Not in our most powerful colliders, so we simulate it with supercomputers and equations. We take quantum mechanics and general relativity and push them to their breaking points. See what they predict. These theoretical models are our only window into that impossible interior. They show how the crust fractures, how the magnetic field snaps, how the energy transforms. Each giant flare we see is a data point, a cosmic experiment. It either confirms our theories or forces us to rewrite them. The Magnetar, in its violent silence, is asking the deepest questions about matter, energy, and force, and with each eruption, it offers a piece of the answer. Scientists are trying to build a model of this explosion from impossible conditions. They're working out the sequence from the first bit of stress to the final flash. There's one leading idea, the twisted magnetosphere model. You have these magnetic field lines anchored deep in the star's core. They come up through the superfluid and go right through the solid crust. Now imagine that crust shifts just a little. It's under huge strain. The footpoints of those field lines get dragged. Over years, maybe decades, the external magnetic field twists up. Like winding a rubber band around a ball, tighter and tighter, energy builds in that twisted bundle. The stress on the crust underneath becomes too much. The crust fractures, the magnetic band snaps, all that stored energy is released in a catastrophic reconnection. Another theory looks deeper down: magnetic buoyancy. Inside the star, you have bundles of magnetic flux, like tubes of intense force. They're created by the dynamo in the turbulent fluid. They're strong, so they're buoyant. They want to rise like a hot air balloon. These flux tubes fight their way up through the dense nuclear matter. When one finally breaks the surface, it erupts. It's a magnetic volcano. This new magnetic loop comes out and violently interacts with the star's existing field. That's another way to get a sudden, explosive reconnection. Building a computer simulation for this is a monumental task. It's not one branch of physics. It's 3 or 4, all at their most extreme. You need general relativity for the crushing gravity that shapes the star. You need quantum electrodynamics to model how light and matter behave in those quadrillion-strength magnetic fields. And you need nuclear physics for the crust and the superfluid sea beneath it. Getting these codes to talk to each other, to make one picture of a starquake, pushes our best supercomputers to their limit. Recent breakthroughs in these simulations show a terrifying chain reaction. A local crust crack doesn't stay local. The initial fracture sends a shock wave around the star's surface at a significant fraction of light speed. This global seismic wave shakes the entire magnetosphere violently. It's like ringing a bell, but the bell is made of pure magnetic force. That global disruption can trigger reconnection events at multiple points at the same time. A small break becomes a worldwide magnetic storm on the surface of a dead star. The ultimate test for any theory is in the light we see. Astronomers build these complex models to get a prediction, a specific pattern for how the flare's brightness should rise and fall, and what colors or spectra it should show. This predicted light curve gets held up against the actual data from events like the Christmas star of 2004. Often, there's a match in the broad strokes. But the data always brings surprises: a flicker in the tail of the emission, an unexpected spike in a certain energy band. These are the clues, the wrinkles in reality that tell the theorists their model is close but not quite complete. Each surprise is a gift. It forces a refinement, a new layer of complexity, a deeper question about the true nature of matter under siege. That flash is just the beginning. What follows is a ghost, a rhythmic pulse that fades over minutes. This is the afterglow. It holds the star's secrets. After the explosion tears the crust open, it creates a fireball. A bubble of superheated plasma and radiation, and it's trapped within the Magnetar's own magnetic field. The fireball is caught. It bounces between the magnetic field lines that loop from one pole to the other. Like a sound wave echoing, but this echo is pure energy, and the Magnetar is spinning, so that trapped fireball gets beamed toward us with every rotation. We see it as a pulse, a cosmic lighthouse blinking from the wreckage. That pulse is a gift. It's a direct measurement of the star's heartbeat. By timing the interval between each flash, they can clock the Magnetar's spin. Down to the millisecond, but the data goes deeper. The way the light fades, the subtle changes in the pulse shape over time. These are clues about the magnetic field's geometry. The fireball is illuminating the structure of its cage. Is the field a simple dipole like a bar magnet, or is it twisted and tangled from the starquake? The afterglow's behavior paints that picture. It lets scientists map the invisible architecture, the force surrounding the dead star. The light itself carries a fingerprint. Its spectrum, the distribution of energy across different wavelengths, it tells a story about the plasma, how dense it is, how hot it got. From this, researchers can estimate the total mass. The mass of material ripped from the star's surface. They can trace how that ejected cloud expands and cools in the minutes after the eruption. This lingering echo turns a millisecond of violence into a prolonged session. A diagnostic session, a single event becomes a detailed report on the star's magnetic field, its rotation, the physics of its shattered surface. This understanding turns our gaze backward. Backward in time, before satellites, before we knew what a magnetar was. Observers sometimes recorded strange, sudden stars, brief, brilliant points of light that appeared and vanished. Now, with the template of a modern giant flare, that sharp spike and pulsating tail, historians and astronomers can re-examine those records. They can look for descriptions that match the profile. A star that flared with incredible brilliance and then seemed to throb or fade in a rhythmic way. It's a new way to read the old sky, searching for echoes. Echoes of stellar catastrophes witnessed by civilizations long gone. The afterglow is more than a fading light. It's a key. It unlocks the present mechanics of these monsters. And it helps us find their footprints in our past. A reminder that the sky has always held these sleeping giants, occasionally stirring in their magnetic slumber. The Star of Bethlehem, a story from 2,000 years ago, a star that appeared, guided travelers, and then vanished. Modern astronomy has explanations. A planetary conjunction, a comet, a nova, but some accounts describe a sudden, incredible brilliance that's led a few scientists to a more dramatic idea. Could it have been a giant flare from a nearby magnetar, a flash so intense it outshone every star in the sky for one night, then faded? It's a speculative thought. A cosmic cataclysm woven into human history. It makes you look at old stories differently, wonder if our ancestors saw events we now know are possible. This search goes beyond texts. It goes into the planet's own archives. In the late 1970s, scientists studying ancient tree rings found something, a sharp spike in radioactive carbon-14. Dated to the years 774 and 775 AD, this carbon-14 is created when high-energy radiation from space hits nitrogen in the upper atmosphere. The spike was global. Massive, something had bathed the Earth in an intense wave of radiation around that time. The leading suspect is a cosmic gamma-ray burst, possibly from a magnetar flare within our own galaxy. The event wasn't bright enough to be seen in the daytime sky, but its invisible radiation left a permanent mark in the growth rings of every living tree. A silent witness to a stellar eruption over 1,200 years ago. This is forensic astronomy, astrophysics meeting archaeology and history. Researchers now scour Antarctic ice cores, looking for matching spikes in beryllium-10. Another isotope created by cosmic rays. They comb through records from medieval monks and scholars, searching for any mention of strange red skies, unusual auroras, sudden unexplained stars. Each potential correlation is a clue, a piece of a puzzle that stretches across disciplines. It extends our observational timeline of the cosmos back thousands of years. Far beyond the invention of the telescope, we're no longer limited to what we can see today. We can search for what the Earth itself has recorded. These investigations turn our planet into a giant cosmic dosimeter. A device that's been quietly measuring extreme events from space for millennia. Finding a clear signal is incredibly difficult. A single tree ring spike could have other causes. An extreme solar superflare, but the work continues because the stakes are profound. By building a historical record of these cataclysms, we can better understand their frequency. We can ask how often our solar system has been brushed by the dying breath of a distant star. This long-term view is crucial. It provides the context we need to assess the true rhythm of galactic violence. It prepares us to look forward with our modern satellites and sensors, knowing what to listen for. The past isn't just a story, it's data. And in that data, we might find the key to predicting our place in a galaxy that occasionally remembers how to shout. We have these listening posts now, electronic eyes watching the dark. It's not one telescope, it's a whole network. Instruments in orbit, instruments on the ground, all listening for the high-energy signals from space. There's NASA's Swift Observatory. Swift is the rapid responder. Its burst alert telescope is always scanning, watching over a sixth of the sky at any moment, looking for the flash of a gamma-ray burst. When it sees one, the whole spacecraft can turn toward it in under a minute. It finds the location and sends that position out immediately to observatories everywhere. Swift is the first alert, the shout that goes out. Then NASA Fermi telescope joins in. Swift is agile, but Fermi is a powerhouse. Its large area telescope looks at the whole sky every 3 hours, but in gamma rays the highest energy light there is. When a Magnetar erupts, Fermi measures the full spectrum of that blast. It breaks the light apart. It tells scientists not just how bright it was, but what particles were in it, how they got accelerated to those impossible speeds. Fermi's data is like a chemical analysis of the explosion. Closer to us on the space station, there's another instrument, NICER, the Neutron Star Interior Composition Explorer. Its main job is to study the steady glow of neutron stars, to map their hotspots, measure their incredible density. But when one of these objects erupts, NICER catches the aftermath in fine detail. Its X-ray timing is so sensitive it can track the vibrations of the star itself in the pulsating tail of a giant flare. It's listening to the ringing of the bell. On the ground, there's a different kind of ear, big arrays of radio telescopes, like the Very Large Array or the Future Square Kilometer Array. They sometimes catch the steady, faint pulses of a magnetar's normal spin. These radio whispers help complete the picture. They give another way to measure the magnetic field strength, the star's rotation. They're the baseline. The quiet heartbeat that makes the sudden cardiac arrest of a flare stand out. And soon a new eye will open, the Vera C. Rubin Observatory being built in Chile. It will start the legacy survey of space and time. Every few nights, it will image the entire visible southern sky. It won't just look for known objects, it will search for change. For anything that moves or flickers or flashes. That relentless pace means it could catch the optical light from a distant magnetar flare, a rare glimpse. It will turn the sky into a movie, and we'll be watching for the next frame where a star suddenly remembers its power. This global network does more than just catalog explosions. Each giant flare it records is a natural experiment, physics under conditions we can never recreate. The light that travels for millennia to hit these detectors carries encoded information. Information about how matter behaves in magnetic fields a quadrillion times stronger than Earth's. It tests our theories, quantum electrodynamics and general relativity, pushed to the extreme. So every alert, every data stream is a message about the limits of reality, sent from a laboratory we will never visit, but whose results we are now starting to read. That lab in space is testing the laws of physics. Einstein's theory of gravity, general relativity, describes how mass warps space and time. We've confirmed it around stars like our Sun. But a magnetar's gravity is different. It's so intense that space-time is twisted into a much more severe shape. The flares can probe this. The radiation, as it escapes from just above the star's surface, has to climb out of that deep gravitational well. It loses energy, it shifts to longer wavelengths. This effect is gravitational redshift. It's measurable in the flare's light. It tells us if relativity still holds when gravity is at its absolute extreme, near the theoretical limit of what a stable object can withstand. A single flash becomes a stress test for our most fundamental theory of the cosmos. At the same time, the magnetic fields challenge another pillar, quantum electrodynamics. The theory of how light and matter interact. In a magnetar's field, the rules change. The vacuum of space itself becomes polarized. It behaves like a prism for high-energy light. The creation of matter from pure energy, particle-antiparticle pairs, happens at an insane rate during a flare. By studying the specific energies of the X-rays and gamma rays produced, physicists look for deviations. Any anomaly could signal new physics. It could hint at exotic particles or forces we haven't yet imagined that only reveal themselves in these impossible conditions. This search even extends to dark matter. We know it exists by its gravitational pull, but we don't know what it's made of. Some theories propose dark matter is composed of weakly interacting massive particles or actions. A magnetar's colossal magnetic field could be a perfect trap. If these hypothetical particles exist, they might convert into detectable photons within the field. Or the intense environment of a flare could produce them. While no signal has been found, magnetars offer a natural, high-energy experiment to look. They turn the entire star into a detector for the universe's most elusive substance. Beyond testing theories, these flares are practical tools for cosmic cartography. In visible light, we use certain stars' Cepheids variables as standard candles to measure distances. Their known brightness lets us calculate how far away they are. At the highest energies, magnetar giant flares might serve a similar purpose. The physics of the explosion suggests there's a maximum intrinsic brightness they can reach. If we can confirm that limit, then measuring how dim the flare appears from Earth gives us its distance. This is crucial for mapping the universe in gamma rays, a light that cuts through cosmic dust, letting us gauge the scale of our galaxy and beyond with new precision. Every observation from these magnetic monsters pushes at a boundary. The data either fits our models, confirming we're on the right track, or it contains a strange spike, an unexpected fade, a pulse that shouldn't be there. Those are the moments scientists live for. They are the fingerprints of the unknown, a hint that our understanding of matter, energy, or space-time is incomplete. Magnetars have transformed from celestial oddities into essential probes. They are our remote laboratories for conditions that will never exist on Earth. With each eruption, they ask the universe a profound question, and the answer, written in radiation, helps us write the next chapter of physics. The most powerful explosions in the universe might have a common heartbeat. Gamma-ray bursts, they're these cosmic cataclysms so bright they can outshine a whole galaxy for a moment. There are two kinds, short and long. The long ones, the ones that last from a couple seconds to minutes, they've been a real mystery. They mark the death of a truly massive star, but the physics of that final act, it's been debated. There's a compelling theory. It points to a familiar culprit just born. So picture a star many times more massive than our Sun reaching its end. Its core collapses, but not into a black hole right away, into something else first. A proto-neutron star, spinning hundreds of times a second, wrapped in a magnetic field of unimaginable strength. For a brief, violent window, this newborn object is a magnetar. And in this model, it's the engine of the apocalypse. This infant magnetar doesn't just sit there. Its rapid spin, its colossal magnetic field, they act like a cosmic turbine. They funnel the energy from the collapsing star, funnel it into two narrow, opposing jets. These jets, moving at over 99% the speed of light, they drill their way out. Through the dying star's outer layers, when they finally break free, they blast into interstellar space. That breakout, that's the gamma-ray burst we see. A concentrated beam of pure energy screaming across the cosmos. So the long GRB, it isn't just a supernova. It's a supernova turbocharged by a magnetar's birth. The magnetar is the central engine, the power source for the most brilliant flash in the modern universe. Evidence for this idea comes from after the initial flash fades. The afterglow of a long GRB, seen in X-rays and visible light, it often shows a peculiar pattern. Instead of fading smoothly, the light curve has these plateaus. Gentle declines that last for hours, even days. It's as if someone is keeping the fire stoked. That's the signature of ongoing energy injection. Something at the heart of the explosion is still pouring power into the blast wave long after the first detonation. A newborn black hole would swallow everything. but a magnetar, a massive, spinning neutron star, it's perfect for the job. As it spins down, its rotational energy converts into magnetic winds and radiation, pumping energy into the expanding debris. That sustained power, that's the telltale clue. Some observations go further. In the afterglow light of a few specific bursts, astronomers have identified faint, rhythmic flickers, a slow, steady pulsation embedded in the fading fire. This is the holy grail of evidence. It suggests a central object is indeed spinning, and its lighthouse beam is periodically sweeping across our line of sight. A direct detection of the Magnetar engine itself, still working amidst the cosmic wreckage. While rare, these findings bridge two fields of study. The isolated, flaring Magnetars in our own galaxy, they're the middle-aged versions. The long gamma-ray bursts in distant galaxies, they show us their violent birth. It's a life cycle of magnetic fury. This connection reveals a continuum of cosmic violence, from the starquakes of a solitary, aging Magnetar in the Milky Way, to the earth-shaking birth scream of a Magnetar driving a gamma-ray burst in a galaxy billions of light-years away. The same fundamental physics, a neutron star with a magnetic field wound beyond comprehension. It manifests on scales from the local to the truly cosmological. It tells us the universe has a preferred method for its greatest outbursts. It starts with a twist, a spin, and a magnetic field strong enough to bend the rules of reality itself. The universe has these brilliant explosions. They might be its most efficient messengers. For more than a decade now, a new kind of signal has been coming in from deep space. Fast radio bursts, they're exactly what the name says, incredibly brief flashes of radio waves. They last just milliseconds, but in that tiny window, they release as much energy as our sun puts out over 3 days. They come from far beyond our galaxy, billions of light-years away. For years, their source was a major puzzle. Supernova, black hole mergers, even alien civilizations were proposed. But in April 2020, the answer came from a familiar, violent neighbor, a Magnetar in our own Milky Way. SGR 1935 plus 2154. It erupted. It produced a powerful X-ray burst like the flares we've talked about. And at the exact same moment, telescopes on Earth detected a millisecond blast of radio waves. A fast radio burst from our own galactic backyard. That was the first direct link. A smoking gun, the theory for how a Magnetar creates an FRB, is a piece of extreme physics. It starts with the Starquake, the initial magnetic explosion. That flare accelerates a storm of particles to nearly light speed. But this storm doesn't just fly off into empty space. It slams into the dense, magnetized debris around the Magnetar. Material left over from its supernova birth or from previous eruptions. That collision is chaotic. It creates a turbulent, electrified plasma, and within this maelstrom, something special happens. The particles get organized. They start to move in sync, like a school of fish turning as one. This phenomenon is called coherent emission. Instead of radio waves spraying out randomly, they amplify each other. They become a focused, laser-like beam, a single, intense pulse of radio energy that can punch across the universe. So the same crust-shattering event that makes the X-ray flare also sets the stage for the radio burst. It's a two-part performance. This connection, if it holds for the distant FRBs, would solve a major mystery. It would mean Magnetars aren't just producers of high-energy violence. They're versatile cosmic beacons. Their influence spans the entire electromagnetic spectrum, from the deadly gamma rays that could sterilize a planet to the radio whispers we can tune into with our dishes. It suggests a single class of object born from the death of massive stars can account for a stunning array of signals, from the soft gamma repeater bursts in our galaxy, to the giant flares that light up other galaxies, to the mysterious millisecond radio chirps from the cosmic frontier. This versatility forces a comparison. We once thought different cosmic beasts ruled different domains: supermassive black holes for quasars, neutron star mergers for gravitational waves, supernova for visible light. But Magnetars are emerging as potential unifying players, a single, city-sized engine capable of generating a portfolio of cosmic transients. Their power comes from a combination of factors nothing else has. That insane density, the fastest spins in the universe, and magnetic fields at the absolute limit of physics. This trio creates a natural laboratory for particle acceleration and radiation mechanisms we're only starting to understand. Each detected FRB, especially the ones that repeat, gives us another data point, another chance to decode the precise recipe that turns a magnetic convulsion into a clean, bright radio signal heard across billions of light years. The hunt is on now to catch more Magnetars in the act, to see if this two-part signature is a rule or a rare exception. That versatility means you have to rank cosmic power. To see where Magnetars stand, you put them next to the other titans, the supernova and the black hole. Each one masters physics in a different way. A supernova is a massive star's final act. It's a total demolition. Over weeks, it releases a staggering amount of energy, something like 10 to the 44 ergs. That energy is the kinetic force of the blast. It's the light and heat that outshines whole galaxies. It's a slow, majestic release. It scatters the elements for life across space, but it takes its time. A Magnetar giant flare works on a different clock. It can deliver a similar total energy, 10 to the 44, even 10 to the 46 ergs, but it doesn't do it over weeks. It does it in milliseconds. It's not a demolition, it's a detonation. All that power is concentrated into one point of radiation, unimaginably bright. It's the difference between the sustained roar of a waterfall and the instantaneous crack of lightning. Both are powerful, but one is focused violence. Then there's the black hole, specifically the supermassive black hole at a galaxy's center, feeding on an accretion disk. That process can be the most persistently luminous thing we know. A quasar can outshine 1,000 galaxies for millions of years. Its power source is gravity, pure, relentless gravity, converting the infall of matter into blinding radiation. It's a steady cosmic furnace on an incomprehensible scale, but it lacks the sudden punch. A black hole accretion event is a marathon. A Magnetar flare is a 100-meter sprint run in a picosecond. They specialize in different forms of energy. Magnetars are the champions of magnetic energy release. They take the rotational energy of a collapsed star and, through twisted fields, convert it into a focused blast. Particles and light, black holes are the masters of gravitational potential. They take the mass of entire stars and convert it, with terrifying efficiency, into radiation as matter spirals in. This comparison isn't about picking a single winner. It's about mapping the energy budget of the cosmos. The universe uses different engines for different tasks. Supernova are the recyclers, the great dispersers. Black holes are the regulators, the gravitational anchors that shape galaxies over eons, and Magnetars. They are the punctuators, the exclamation marks. They remind you that magnetic forces, wound tight enough, can briefly rival gravity's raw power. They dominate in the realm of the sudden and the extreme. In the milliseconds that can illuminate the dark for light years. Understanding their roles is like understanding instruments in an orchestra. The supernova is the timpani roll. The black hole is the sustained note of the cello, and the Magnetar flare is the shocking strike of the cymbal. Each one defines the cosmic symphony in its own way. Unlike any instrument, these magnetic dynamos can't play forever. Their furious energy has to fade. The cymbal's strike fades, and the instrument itself changes. A Magnetar isn't a permanent state. It has a life story, a journey from a violent birth toward a slow, magnetic quiet. It starts in chaos. In the first few thousand years after the supernova, the newborn Magnetar is hyperactive. Its magnetic field is at its absolute peak, wound impossibly tight from the collapse. The solid crust, freshly formed, is under maximum strain. This is the era of frequent starquakes. Constant small bursts, the object is settling down. Its crust cracks and heals as it finds a new equilibrium under that titanic magnetic pressure. We're seeing the stellar remnant's turbulent adolescence. A phase of intense growing pains. Over time, the very source of its power begins to fade. The monstrous magnetic field is not eternal. It decays. Through ohmic dissipation, the electrical currents that generate the field slowly lose energy as heat. And through ambipolar diffusion, where particles drift in the superfluid core, the field untwists, it weakens. This decay is slow on a human scale, tens of thousands of years. But it is relentless. As the field strength drops, the stress on the crust lessens. The starquakes become less violent, less frequent. The giant flares, those millisecond cataclysms, become rare events. Separated by centuries or longer, the Magnetar is entering middle age, its fiery temper cooling. What comes after is a long, quiet retirement. After perhaps 100,000 years, the magnetic field may decay to the level of an ordinary neutron star. A pulsar, the star no longer has the magnetic muscle to fracture its own crust, to power giant flares. It becomes a more predictable cosmic lighthouse. Beaming out radio waves powered by its slowing spin, it continues to cool, radiating away the heat from its birth and its magnetic decay, fading into darkness over millions of years. This is the presumed end state, a cold, dense cinder, a silent monument to a once unimaginable magnetic force. But that classic story may not be the only path. An intriguing open question hangs over this life cycle. Can a Magnetar be reborn? Is this magnetic death a one-way street? Some theorists speculate. A dormant neutron star could be re-energized. Perhaps through the accretion of matter from a companion star. As material spirals onto its surface, it could spin the star up again, potentially reignite a dynamo in its interior, twisting a strong magnetic field back to life, or maybe through a different internal phase transition in its ultra-dense core. The idea is controversial, but it suggests magnetic fury might not be a single youthful phase. It could be a cycle. A star might sleep for eons, only to have its magnetic heart shocked back into action. This life cycle perspective is crucial. It frames the incredible flares we witness not as random acts of cosmic violence, but as a specific, fleeting chapter. We are catching these objects in a brief window of spectacular activity, a window that lasts for a mere blink in galactic time. Our entire recorded history is a snapshot within that blink. To see a giant flare is to witness the peak of a magnetic star's life, a temporary and extreme state of being. It makes our detection of them feel even more remarkable. We are not just observing distant explosions, we are glimpsing the intense, formative years of stellar corpses, a phase that will inevitably pass, leaving behind a quieter, darker universe. This realization shifts the question from what they are doing now to what they leave behind, what silent legacy their furious youth creates in the galaxy around them. But isolation isn't the only story a Magnetar tells. Some of these magnetic monsters might not be alone. You could have a Magnetar locked in a gravitational dance with another star. A binary system, and that's a recipe for even greater violence. The companion star, maybe a normal star, maybe another dense remnant, becomes a source of fuel. A source of instability. Gas from the companion can flow onto the Magnetar's surface. That process is called accretion. It's not a gentle rain, it's a torrent of matter slamming into an already stressed crust. And that incoming material carries its own magnetic field, its own angular momentum. As it spirals in, it can twist the Magnetar's already unimaginable field. Twist it into even more complex, stressed configurations. It's like winding a spring that's already at its breaking point. That added stress could trigger more frequent starquakes. Or, in a catastrophic scenario, it could lead to a flare of unprecedented power, one that dwarfs even the giant flares we've seen from solitary magnetars. The binary partner essentially pours gasoline on a magnetic fire. There's an even more extreme possibility: a merger, two neutron stars, one a magnetar, spiraling together after billions of years in a decaying orbit. Their final collision would be one of the most energetic events in the universe. For a fleeting moment, the merged object could be a hyper-massive neutron star. A bizarre, magnetized blob of nuclear matter spinning thousands of times per second. Its magnetic field, a combination of the two progenitors, would be indescribably tangled and strong. And this object would be supremely unstable. It might last for only a few hundred milliseconds before its own gravity wins, and it collapses into a black hole. But in that brief, shining moment, it could power something we've detected from across the cosmos: a short gamma-ray burst. The incredible magnetic turbulence and particle acceleration during that collapse could beam a final, focused scream of gamma rays across the universe. So in this model, a binary magnetar merger isn't just an end. It's the trigger for a different kind of cosmic cataclysm. These binary interactions introduce wild cards. New variables of mass, spin, magnetic geometry. They create systems where energy isn't just coming from the magnetar's internal decay. It's being pumped in from the outside. That turns the magnetar from a solitary, wound-up spring into a component of a far more volatile engine. The potential for unpredictable, luminous events skyrockets. We haven't definitively confirmed a magnetar in such an active, mass-transferring binary yet, but the theory is robust. We see other neutron stars in these setups, and we know the physics scales with magnetic field strength. Finding one would be a watershed moment. It would open a new window into how magnetic fields evolve under the extreme duress of a cosmic partnership. Studying these hypothetical systems expands the narrative. Magnetars are not just isolated, ticking magnetic bombs. They can be actors in dynamic, chaotic relationships. Their story becomes one of interaction, of gravitational give and take that can twist fate toward even greater outbursts. It suggests that the universe's most magnetic objects might sometimes find partners in chaos, creating alliances that push the very limits of energy release. And that shifts our search. We have to listen not just for the solo performances of these stellar corpses, but for the potential duets, for the synchronized and far more destructive dances in the dark. That data from the 2004 eruption, it's not just a graph. You can hear it. Scientists and artists took the numbers, the exact intensity of the X-ray flux during those minutes, and turned them into sound. That's sonification. Making the invisible audible. That first catastrophic spike, the giant flare, becomes a single deafening crack, a digital thunderclap that overloads the speakers. Then the data moves into the afterglow and the sound changes. It becomes a rhythmic beat, a deep thump that echoes the star's rotation. Each thump is a pulse of light turned into a pulse of sound. And as the afterglow fades, the beats slow down. They get softer, more spaced apart, until they dissolve into a quiet hiss, cosmic static. Listening to it is eerie. You're hearing the death rattle of a star's magnetic field, the ringing of a bell 20,000 light-years away. But this translation, it does more than make a compelling sound. It reveals things. Our eyes are good at spotting certain patterns, but our ears are wired for rhythm, for subtle changes in pitch. In the sonified data, a slight irregularity in the decay might stand out as a waver in the tone. A harmonic buried in the noise could become a clear, high chime. Features a scientist might miss on a plot, but they're unmistakable when you hear them. It's a different way of knowing. The universe communicates through energy, and energy is vibration. Whether that vibration is gamma rays or sound waves, that's just a translation. Projects like this bridge a divide. They connect the abstract, mathematical world of astrophysics to the intuitive, sensory world of human experience. It's science as a form of art, and art as a tool for discovery. By giving a voice to these silent explosions, we engage with them on a more visceral level. We don't just understand the flare intellectually, we feel its sudden violence, its lingering decay. This approach embodies a modern quest to comprehend the incomprehensible. When the numbers are too big, the distances too vast, the forces too alien, we find new languages. We turn light into sound. We listen to the stars, and in their echoes, sometimes we hear the answers. Hidden in plain sight, that silent crack in the crust, the Starquake, there might be another witness. Neutrinos, they slip through everything. When the Magnetars' iron lattice fractures, the shuddering of that hyper-dense matter should produce a brief, intense shower of these particles. Neutrinos are almost massless. They carry no charge. They barely interact with normal matter. For them, the entire star is nearly transparent. So the gamma-ray flash is trapped, bounced inside the magnetic cage, but the neutrinos escape instantly. They race out at light speed. They carry a pristine snapshot of the conditions inside the star at the exact millisecond of the quake. Messengers from the heart of the cataclysm, untouched by the magnetic maelstrom. Catching them is the challenge. On Earth, we have detectors buried deep in ice under mountains, like the Ice Cube Observatory at the South Pole. Thousands of optical sensors frozen into a cubic kilometer of ice, waiting for the rare moment a neutrino interacts and produces a faint blue flash. If a magnetar in our galaxy had a giant flare, the models predict a neutrino burst that should, in principle, be visible to Ice Cube, a whisper of light in the dark ice, coinciding perfectly with the blinding gamma-ray screams seen by satellites. That simultaneous detection hasn't happened yet, but the hunt is on. Achieving it would change everything. It would be the dawn of true multi-messenger astronomy for these events. We wouldn't just be studying the light from the explosion's aftermath. We'd have a direct signal from the engine room itself. The properties of the neutrino burst, its energy, its duration, would be a direct report on the nuclear physics of the fracturing crust. It would tell us about the temperature and density at the fracture point in a way light never could. It would constrain the equations of state for matter under that extreme pressure. This data would be a Rosetta Stone, decoding the violent language of the star's interior. The dream extends further, to combine three cosmic messengers at once. The neutrinos from the core, the gamma rays from the magnetic explosion, and perhaps one day the faint ripples in space-time gravitational waves from the global shudder of the Starquake itself. A triple detection, a complete three-dimensional picture. Each messenger reveals a different layer. Gravity reveals bulk motion, light reveals electromagnetic fury, and neutrinos reveal the hidden nuclear fire. It would be like seeing, hearing, and feeling an explosion from across the galaxy all at once. This isn't just a technical goal. It's a fundamental shift in how we understand cosmic violence. Moving from observing the outside of these magnetic monsters to taking their internal pulse, every major observatory campaign plans with this possibility in mind now. They synchronize watches across the electromagnetic spectrum with neutrino and gravitational wave detectors, preparing for the next galactic shout, hoping it brings a ghostly whisper and a subtle tremor. Waiting for the day the silent witnesses finally speak. They're recreating starquakes here on Earth, not in a lab, inside supercomputers. These are massive machines, thousands of processors working together at places like NASA Ames or the national labs. Their job is to simulate the exact instant a magnetar's crust shatters. To do that, scientists build huge three-dimensional models. They're called magnetohydrodynamic simulations. That means they combine magnetism, fluid dynamics, and extreme matter behavior all at once. You start with a virtual neutron star. Its crust is modeled as an elastic solid, a lattice of iron nuclei under incredible strain. The interior is a superfluid sea, and through it all, a magnetic field of ludicrous strength twisted into knots. Then the simulation applies stress. Maybe the drag of the superfluid core on the crust, or the slow winding of the external magnetic field. The digital crust deforms, and then, at a critical point, it fails. A fracture starts. On a screen, it might look like a glowing red line spreading across the star. But this isn't just a crack in rock. As it moves, the simulation calculates how it shakes the magnetic field lines anchored to it. You can see them in the visualizations like elastic bands stretched to the limit. They writhe and snap. Where they break, they reconnect in simpler shapes, releasing a torrent of digital energy. That's magnetic reconnection, rendered in detail. These visualizations turn an abstract equation into something you can see, a mechanical break becoming an electromagnetic cataclysm. This digital work is a playground for astrophysicists. They can test different triggers. What if the star spins faster? What if the magnetic field is twisted differently? They run the simulation hundreds of times, change variables, watch what happens. Each run predicts specific observable signatures, maybe the exact shape of the gamma ray light curve, how fast the flare spikes and fades, or the specific frequencies the star should ring at afterward. These predictions go to real telescopes. When a magnetar erupts, astronomers compare the actual data to the simulation library. It's a constant refinement. A mismatch means the simulation's physics is incomplete. Maybe the crust is stronger. Maybe the magnetic field reconnects a different way. So the theorists go back, tweak the code, run it again. This cycle theory, computation, observation, that's modern astrophysics. We're not passive observers of these distant explosions anymore. We're active participants, using silicon and code to ask the universe questions and interpret its answers. The supercomputer becomes a digital oracle, letting us safely detonate a star over and over to find a single truth: how matter behaves when every rule we know is broken. We know a lot about magnetars, but there are still deep mysteries. The first is what's actually inside them. We have models: a solid crust, a superfluid sea, maybe a quark soup core, but those are just guesses. We don't know the precise arrangement of matter under that kind of pressure. Does the crust float on the superfluid like a shell, or is it threaded through with neutron vortices? That answer changes how starquakes move and how the magnetic field is anchored. We just can't see inside. Then there's their behavior. Why do some magnetars, like SGR 1903+25, have frequent, smaller bursts for years, while others, like SGR 052666, stay silent for decades? Is it age, magnetic field geometry, leftover supernova debris? We don't have a clear system to predict which sleeping giant will stir next. Their personalities seem unique. And then there's the ultimate limit. Theory says a magnetic field can only get so strong before it starts to alter the vacuum of space itself. That's the quantum critical limit. The field's energy density gets so high it spontaneously creates particle pairs from nothing. Have we seen a magnetar at that extreme? Or is there a ceiling the universe never lets an object reach? Finding one at that boundary would change quantum physics. We also don't know how often they truly awaken across cosmic time. Our historical record tree rings, ice cores, suggests a major event might brush Earth every few thousand years. But across the whole universe, in much older galaxies, how often do these magnetic eruptions happen? That rate dictates their role in shaping galactic chemistry, maybe even seeding heavy elements. It's a census we're just starting. Each of these questions is a frontier. Answering them might not come from small steps, but from a sudden leap. a lucky observation from a new telescope catching a flare in a new wavelength, or a theoretical insight that reimagines matter under conditions we can only write equations for. This not knowing isn't a failure, it's the engine of science. It means our current understanding, however detailed, is provisional, a map that's still being drawn, and it's that humility that drives the next generation of tools, instruments, built not just to see better, but to listen for answers we haven't even learned how to ask yet. The next generation of eyes on the sky is already being built. The European Space Agency has a plan for the 2030s to launch a new kind of X-ray observatory. Called Athena, it's designed to see with a clarity we've never had. So when a Magnetar flares, Athena won't just measure the brightness, it will dissect the light. Take the X-ray spectrum and split it into thousands of distinct energy channels. It's like listening to a symphony and suddenly being able to hear every single instrument, every note with perfect separation. That detail will show us the temperature of the plasma fireball, the density of the ejected material, the precise strength of the magnetic field that shaped it. Athena will turn a brilliant flash into a detailed report, a chemical and physical report, telling us exactly what was created and destroyed in that millisecond of violence. On the ground, a different kind of ear is taking shape, the Square Kilometer Array. It's not one telescope, but a vast network of radio dishes spread across 2 continents. Its sensitivity will be staggering. It will listen for the faint, steady radio pulses from dormant magnetars, mapping their magnetic personalities even when they're quiet. And it will be a supreme hunter of fast radio bursts. If a magnetar in our galaxy produces one of those millisecond radio chirps, the Square Kilometer Array will catch it. With breathtaking detail, it might even catch the very first radio whisper that comes before a giant flare, a clue we've been missing about how the explosion begins. Beyond these confirmed missions, there are concepts on the drawing board. They sound like science fiction. A satellite dedicated solely to the X-ray time domain, watching the sky for flickers and flashes with a speed and precision we can't manage today. It would catch the rise and fall of Magnetar bursts we currently miss, building a statistical picture of their true activity. And then there's the possibility of sensing the Starquakes themselves. Not with light, but with gravity. A future gravitational wave observatory in space, like the proposed LISA mission, could be sensitive enough to feel the ripples from a giant flare in our galactic neighborhood. It would detect the actual shudder of the star's crust, the global ringing set off by the fracture. Combining that gravity signal with the X-ray and radio light would be the ultimate portrait. A multi-messenger portrait, a full body scan of a cosmic catastrophe. These future tools promise a transformation. They will turn magnetars from rare, enigmatic curiosities into routine subjects of study. We'll move from catching occasional, spectacular outbursts to understanding their daily life, their gradual evolution. Within a few decades, these magnetic monsters could become some of the best understood extreme objects in the universe. Open books written in X-rays, radio waves, and space-time ripples. This isn't just about filling textbooks. It's about fueling a deeper curiosity. The more we learn about how matter and energy behave at these limits, the more we refine our understanding of reality itself. The coming era of observation holds the potential to solve mysteries we've wrestled with for decades, and undoubtedly to reveal new ones we haven't even dreamed of yet. Magnetars have this magnetic fury. It tears at space itself, and that same force has sparked stories. They've jumped from science journals into science fiction. Authors and screenwriters love them, that sheer, incomprehensible power. It's a ready-made cosmic threat or a nearly magical energy source. There's the classic novel Dragon's Egg by Robert L. Forward, humans encounter a civilization living on the surface of a neutron star. The inhabitants are called Chila. they experience life at a vastly accelerated rate. Because of the crushing gravity, it's not solely a magnetar, but the novel explores that mind-bending physics, extreme density, magnetic fields. It introduces readers to these concepts through a gripping narrative. It turns astrophysics into a stage for drama, for first contact. Television uses them as engines of apocalypse. In Doctor Who, an episode features a Magnetar's beam. It's weaponized, capable of destroying entire planets. The show uses its real scientific reputation, the intense magnetic field, the radiation, and it scales that into a plot device. The drama isn't in inventing a new threat. It's in taking a real one and asking, what if someone aimed it? This translation from fact to fiction serves a purpose. It wraps complex, intimidating science in accessible packaging. Adventure, conflict. A viewer might not grasp the mathematics of magnetic reconnection. But they understand the stakes when the Doctor has to stop a star from firing a lethal beam at Earth. That emotional hook can be the first step toward genuine curiosity. This cultural permeation is more than entertainment. It's a bridge. By placing Magnetars in stories, creators contextualize that terrifying power. They put it within familiar frameworks. Heroes, villains, survival. It satisfies a deep human urge to frame the incomprehensible into a narrative we can process. The Magnetar is no longer just a data point in a distant galaxy. It becomes a character, a force of nature with personality. This process demystifies the science just enough to invite people in, making the real discoveries feel less like abstract equations and more like chapters in an ongoing cosmic saga. The frightening becomes fascinating. That bridge between hard science and storytelling is now a deliberate tool. In education, teachers and science communicators use the cultural footprint of objects like Magnetars to ignite interest. They might start a lesson with a clip from a show or the premise of a novel, and then peel back the fiction to reveal the even more astonishing truth. The question shifts from could this destroy a spaceship to how does matter actually behave inside one? That shift is powerful. It leverages imagination to fuel a desire for real understanding by meeting students where their interest already lives, in stories of cosmic wonder and danger. Educators can guide them toward the mathematics, the physics, the open questions that define real research. The Magnetar, in all its fictional and factual glory, becomes a gateway. Not just to a single topic, but to the entire scientific method. A reminder that the universe is full of stories waiting to be decoded, and the next chapter is always being written by those brave enough to look up and ask how. That cultural bridge goes right into the classroom. Magnetars aren't just for stories. They're some of the best tools we have for teaching extreme physics. Their sheer outrageousness grabs a student right away. You can start with a simple fact. A single teaspoon of neutron star material weighs as much as a mountain. That's density, a magnetic field so strong it distorts atoms into long needles. That's magnetic force, a flash brighter than a galaxy. That's energy scale. These aren't dry numbers, they're declarations, a universe that operates on rules far beyond what we know. By starting with the mystery, you hook the curiosity first. Then you guide students back into the principles, the ones that make such a thing possible. Planetariums have done this. They create immersive shows. You don't just hear about a starquake, you see a visualization. That iron crust, 100 trillion times stronger than steel, buckling. You hear the simulated sound of the data. The deep thump of the afterglow pulses. It makes the invisible forces feel visceral, tangible. After that, the equations are no longer abstract symbols. They're the blueprints for that spectacle. They're the answer to the question, how can that even happen? Interactive simulations take it further. Imagine a student at a terminal. They control the parameters. They can increase the spin of a virtual neutron star, wind up its magnetic field, then click to simulate a crustal fracture. They watch their actions trigger a cascade, a crack spreads, magnetic lines snap and reconnect, a graph on the screen spikes, representing the release of more energy than the sun produces in 10,000 years. That hands-on work demystifies the chain. It connects a simple mechanical break to a universe-shaking flash. It shows physics as a dynamic system, not a list of facts. The study of a magnetar is inherently interdisciplinary. It's a perfect case study for how fields connect. To understand it, you need astronomy to observe it. Nuclear physics to model its interior, particle physics to describe the matter and antimatter created in its magnetic maelstrom, and Einstein's theory of general relativity to explain its gravity. How it bends light and time. A single object becomes a nexus, a meeting point for different branches of science, branches often taught in isolation. This shows students that real discovery doesn't happen in a vacuum. It happens at the intersections. It requires collaboration, a shared language. This value points to a deeper truth about fundamental research. We don't study magnetars just to catalog exotic stellar corpses. We study them because they are natural laboratories. They challenge our understanding of reality itself. The knowledge gained there about matter under extreme conditions often finds unexpected uses. Insights into plasma physics and magnetic confinement can inform fusion energy research here on Earth. The algorithms developed to analyze their complex signals drive innovation in data science. In computing, the pursuit of curiosity, of simply wanting to know how the universe works, it consistently feeds back into technology, into inspiration, into a more profound grasp of the natural world. By starting with a captivating cosmic mystery, we can lead not just to answers, but to an appreciation for the process of questioning, for the beautiful, interconnected puzzle that science is always trying to solve. This knowledge isn't just for books. It pays off in unexpected ways. The technology built to listen to magnetars doesn't stay in an observatory. The algorithms designed to find their signal in all that cosmic noise, they're masterpieces of signal processing. They have to be. They're looking for a whisper in a hurricane. And those same mathematical techniques they spin off, they help doctors filter clear images from messy MRI data. They improve satellite communications. They sharpen radar systems, trying to see the invisible. It drives innovation that ends up touching daily life. Then there's the computing power. To simulate a Starquake, you need a supercomputer. You need software that can juggle gravity, nuclear physics, quantum electrodynamics all at once. Modeling these extreme events pushes high-performance computing forward. It demands faster processors, more efficient code, new ways to visualize complex data. The tools built for astrophysics become testbeds, advancements that later help with weather forecasting, aircraft design, materials science. We're building better digital brains by trying to understand a cosmic one. Maybe the most profound potential is in energy, the dream of fusion power here on Earth. It relies on containing a star-like plasma inside incredibly strong magnetic fields in a reactor. The fields have to be stable, intense, controlled. Magnetars are nature's ultimate experiment in magnetic confinement. They show us the upper limits of magnetic field strength, the turbulent behaviors of plasma under those conditions. By studying how these natural magnetic bottles work and how they catastrophically fail, we gain fundamental insights. Insights that could, decades from now, inform the design of more stable fusion reactors. We're learning from the universe's own fusion aftermath to maybe master the process ourselves. No scientist studies a magnetar flare to build a better phone. The motivation is curiosity, to comprehend the cosmos. But history shows this kind of fundamental, curiosity-driven research. It consistently seeds the future. The quest to understand the atomic nucleus gave us nuclear medicine and a new understanding of stellar energy. The mathematics of relativity are essential for the GPS in your pocket. Pursuing knowledge about these magnetic monsters, it cultivates a deeper reservoir of human ingenuity. It trains problem solvers to think at the very edge of the possible. It refines our grasp of the physical laws that underpin all technology, seen and unseen. The value isn't in a direct product, it's in the expanded horizon of what we can understand. And therefore, what we can eventually build. Every scientist who looks at these cosmic hazards feels that weight. You have a real threat, but the chance of it happening is so small it's almost zero. Like a nearby Magnetar flare, it would be devastating, but the odds of it happening in our lifetime are astronomically tiny. So how do you talk about that? There's a duty to inform people, to make sure if a real risk does appear, we're ready. But there's also the danger of sensationalism, of headlines that just create fear. The key is in the language of probability. You can't just say something is possible. You have to quantify the chance. Scientists in planetary defense, in cosmic hazard work, they use tools like probabilistic risk analysis. They calculate the odds of an event over a certain time and weigh that against how bad the consequences would be. That turns a scary what-if into a measured statistic. It allows for a rational discussion about where to put resources, about preparedness, instead of just reacting from dread. This connects directly to things like planetary defense against asteroids. The same ethical idea applies. We do sky surveys to find near-Earth objects not because an impact is coming soon, but because the potential consequence is so high that even a tiny probability makes it worth watching. Monitoring Magnetars fits into that same category. It's prudent, long-term stewardship. It's about building a census of the cosmos, understanding its rhythms, spotting any objects that might one day pose a challenge to life here. The resources for this are a form of insurance, a premium paid not out of fear but from a commitment to the future, and this research pushes a deeper question about our place. Are we just temporary passengers on a fragile planet, subject to random cosmic violence, or can we become active participants in our own long-term survival? Studying threats like Magnetar flares is a step toward that second idea. It means acknowledging that wisdom isn't about ignoring dangers because they're far off. It's about understanding them so we can actually see how vulnerable we are. So this scientific work is rooted in an ethical and societal context. It reminds us that exploring the cosmos isn't some detached academic exercise. It's an act of stewardship. Every observation, every simulation, every risk model, it's all part of building a deeper resilience. It's about giving humanity the knowledge to navigate a universe that's breathtakingly beautiful and once in a great while perilous. The goal isn't to live in fear of the sky. It's to look at it with clear eyes, seeing both the wonders and the warnings as we think about the course for the centuries ahead. Looking up at a clear night sky, you see all those points of light, and you know that some of them are these magnetic titans capable of such fury. It creates a shift in perspective. The things that occupy our days, the borders and conflicts that fill our history, they exist on a scale so small it just vanishes against that backdrop. A single ember from a dead star, just for a millisecond, can outshine hundreds of billions of suns. In the face of that, a human life can feel small. Fleeting, fragile, it's a humbling feeling, but within that humility, there's a counterpoint. We are the part of the universe that became aware. We are the universe looking back, asking why. Those lights aren't just distant points, they're questions, and we've built the tools to start answering. The mathematics, the satellites, the computers. To detect a flash of radiation from 20,000 years ago, to decode its physics, to understand the life cycle of what created it, that's a triumph. Not of scale, but of intellect, shared curiosity. It redefines our place. We're not just spectators on a small rock, we're participants in an act of cosmic comprehension. Magnetars show the universe's full character, serene, spinning galaxies and sudden, catastrophic ruptures, delicate gravitational dances and magnetic rage so intense it twists space itself. That's not a contradiction, it's the full spectrum, and our own story mirrors it. Human history is creation and destruction, profound peace and terrible conflict. We contain that same duality, so understanding the Magnetar is more than science. It's a journey to understand a fundamental aspect of the cosmos that we embody. It's a resilient curiosity, one that looks into the heart of a phenomenon that could erase worlds and says, "Tell me how you work." This journey, from tracing a single gamma-ray flash to contemplating our own role, it leads to a synthesis. To gather these threads, violence, beauty, mystery, understanding, to see what pattern they weave about the universe we call home, we started with a flash of light. A gamma-ray scream from a dead star. We went inward from there through the crushing gravity of a supernova's collapse into the heart of a city-sized ember. A place where matter itself is remade. You feel the strain building in a crust of iron, 100 trillion times denser than steel. The magnetic field twists into knots of pure potential energy. And then it all finally snaps, a single starquake. In less than a millisecond, it releases more energy than our sun will produce in 100,000 years. That energy tears through space. These magnetic monsters have many faces. They are destroyers. From a cosmic stone's throw, their fury could reshape a biosphere. And they are creators. Their shockwaves might trigger the birth of new stars. Their violent hearts could forge the heaviest elements. They are unparalleled natural laboratories. They test Einstein's relativity and quantum physics under conditions we can never replicate on Earth. And they are profound mysteries. Their inner workings are still hidden. Their life cycles are only partially mapped. Their explosive signatures connect the cosmos. The same magnetic engine that powers a solitary flare in our galaxy might, at its birth, drive the awesome beam of a long gamma-ray burst in a distant one. The same starquake that shakes the heavens with X-rays can, under the right conditions, broadcast a millisecond radio chirp, a fast radio burst across billions of light years. A single class of object born from stellar death ties together some of the universe's most energetic and enigmatic signals. Every flash of gamma rays we record is a message. A direct communication from a state of matter so extreme it defies earthly intuition. It challenges our models. It pushes our computers to their limits. It forces us to refine our understanding of reality's fundamental rules. With each eruption, we expand our horizons, not just across space, but across the very frontiers of physics. This journey into magnetic extremes is a testament to human curiosity, to our drive to look at the most violent phenomena in the cosmos and not just wonder, but to understand, to decode.